Welcome to the sixth and final part of this tutorial on generative AI, which is about implementations. So LLMs are huge artificial neural networks with the size of millions or billions of connections, parameters of the model. These networks are trained on huge amounts of web data in the order of terabytes. All input-output to and from the LLMs have to be converted from external quantitative counting to an internal quantitative. The quantitative represents real values, scalars, vectors, matrices, and tensors. All internal counting in the LLMs are performed in terms of such entities. The core LLM technology includes the transform architecture and its encoder and decoder variants, that is the principal generative pre-training. The main LLM arguments are described in a separate lecture earlier in this series. Being essentially machine learning applications, LLM systems can be developed and managed by using standard programming languages like Python, Java, JavaScript, C, and C++. ML framework like TensorFlow and PyTorch, and what we call that MLOps platforms, the purpose of which to structure and support the whole development process, called Amazon SageMaker, Google Cloud Vertex, and so on. So there are many tools around for work with the systems. I would say that the early LLM system was a big success, and I could foresee endless application opportunities, which hopefully have been illustrated by this lecture. It was natural that the original main actors were a few big companies started this. They choose a brute force strategy as the mainstream type of application, assuming that a bigger LLM network gives better performance. If you have 1 billion, is better than 1 million. 10 billion are better than 1 billion parameters. So a bigger model is better. And the more training data you train on, the better result. The bigger networks and the more and more user can be accommodated by adding another big data center. So actually, you're running the systems on extensive infrastructures, and they in principle you only add to those infrastructures. You extend them when you grow. So this is, I would say, the brute force model. And of course, I can say none of the assumptions have been proven wrong, because, systems have grown and they've become better. But the scalability and sustainability of the approach can be doubted, both from what they cost in money, in dollars, but also from the point of what effects they give on the environment. So one can say computational power needed for the LLMs can be divided up as follows. The training of models demands the largest computing resources, in particular the pre-training of the large foundational model. Fine-tuning can possibly be managed by less resources. Running of models are in general cheaper. However, they are more expensive than Google search costs. Also, because the systems are becoming multimodal, they're also becoming, even the running have been more expensive due to the amount of data that have to handle in each run. Then one also have to count into the cost that because of these systems run on systems with a lot of hardware resources, these resources are not there forever. They have to be maintained, they have to be changed, they have to be substituted with new hardware, and that is a cost. And some people have estimated the cost of really maintaining and updating the hardware needed for running is 20% of the whole cost for the whole thing, which is it's not zero, it's rather a lot. So actually, typically, these systems have been computed in cloud infrastructures like Microsoft Azure, Google Cloud, Amazon AWS, and so on. It's the concept. The cloud is a nice concept. However, one negative side of the cloud is that you send things to the cloud, and if you have a cloud that works, you get your result, but you have no clue what the effect is from your point as a user. And these cloud infrastructures are not actually in the cloud. They are very much down to earth, because all cloud infrastructures are actually implemented as large data centers spread around the world, comprising thousands of processing units, allowing for massive parallel computations. So, for example, Google Cloud has 130 computing centers, Microsoft 300, Amazon and 900. This means 2026, 33% of data centers around the world will be targeted to AI, which is an immense amount. And in order to speed up all these quantitative computations, as you have heard many times now, what we do in the systems that we internally represent everything with scalars, vectors, matrices, and tensors, and we compute on them. And so therefore, what's happened is that we don't run on CPUs only, we run on special computing devices, graphical processing units, and also what's called tensor processing units. And of course, in order to handle this special hardware, you need also specific programming languages that helps you utilize these resources in an efficient way. As you can see, then the computing centers grow steadily, reaching the size of small towns. The analysis is suitable as the centers also consume electricity and cooling resources of the level of small town. Unfortunately, most server centers currently use fossil energy. The enter contribute with 3% of greenhouse gas emissions on Earth. A study of GPD shows that the average monthly operation consumes 600 million kilowatt of electricity for 1 month, while brushing your teeth is 150 watt hours per month, while cost for a fridge a day is 3 kilowatt. Charging an electric car is 7 to 100 kilowatt hours. So anyway, it's a lot of energy those, and also cooling water consumption. 580 million gallons of water was used in the study for ChatGPT. So that's the consumption. And then the water also then have to be recycled, which is cooling water would be desirable, but this is still rare. But if that is done properly, it will also add to the cost. So, but there are some positive trends here. I mean, moving in a direction where things are done more economically. So one tendency that we already talked about is that it's not only paid systems, proprietary systems, but open source systems. So this means that the open source part of this have meant that more actors can come into play and have better access to this technology and can contribute to the development. And this has in turn led that there are more experiments of people doing smaller systems and so kind of distill and compile systems that can run on smaller smaller kinds of software or hardware. It's also shown that not necessarily everything that is bigger is better. So there are examples for the Alpaca model that has shown that they can have some really good results with smaller model size. That means less parameters. So many models are now offered in various sizes. So you can run some models. You can run some part as in the cloud, and then you can run other parts on the edge. I would say one example is how the latest Apple launch have been described in that fashion. Also, algorithm techniques can still be improved, and this is coupled to the open access developments, that the more actors that are let into this field of play, the more people can do improvements and optimizations. One example of this, well known now, is the Chinese DeepSeek system that was run on substantially weaker computing equipment and still produced sufficiently good results. When people talked about AI computers again, which actually means computer that you can run in your local environment and that can accommodate at least middle-sized LLMs, which means that you don't have to, in those cases, use the cloud at all. Also, I would say it's very important when you integrate LLMs in general assistance that you are not sending all requests so your assistant to a expensive computing facility. Some things can be solved very simply in your device and on the edge. But many things together seems that we can foresee a lot of trends that democratize the access to the LLM technology and also makes it more sustainable. Thank you.